Hello, for this worked problem, we've got a 3D equilibrium problem. So in this case, we've got x, y, and z directions that we need to worry about. And how this kind of is set up, we've got a flat steel sign kind of hanging out, and it's in the xy plane. So this is a 12-inch by 24-inch flat steel sign with a weight of 10 pounds. This sign, there's now a wind force pushing on the sign in the z direction. And so based on this force in the z direction from the wind, the sign kind of tilts up at a 10-degree angle. So based on this information, we're asked to find what the magnitude of this wind force must be. So this is going to be an equilibrium problem. We're assuming that the sign is kind of holding steady at this angle, and we need to solve for the unknown, in this case, the force of the wind. We're not going to worry about, we would have unknown forces up here at the top and bottom in the tension, but we're not going to worry too much about that. So, we started an equilibrium problem. Even in 3D, we're going to start by drawing the free body diagram. And in this case, I'm going to kind of draw two free body diagrams, one in the XY plane, and then one actually from the side. It'll be looking in the YZ plane. So you'll see what this means in a second here. So actually, let me keep this here for now. So in the XY plane, this is looking straight onto the sign, where Z would be coming out of the board. It's just going to kind of look normal. So it'll look like a square like this. I'm going to have tension forces. We call it T1 and T2 up at the top. And this will actually, these tension forces are going to be coming out of the board a little bit. And the weight force is 10 pounds, pushing or pulling straight down. And the wind force I'm not going to see actually. It's going to be going straight into the board. So now I'm going to draw it from the side. So this is positive x. This is positive y. From the side, I know it kind of looks like this. So it's tilting back at a 10-degree angle. I know I've got a weight force, so 10 pounds right in the center. I know I have a wind force that's pushing back in this direction. And I need to draw on my axes as well. So in this case, if I'm kind of looking at the side of the sign, Z is actually pushing out that way, and Y again is straight up. And then up at the top, I actually have two forces. I have T1, and kind of right behind it, I would have T2. So there's actually going to be 6 possible equations of equilibrium, 3 forces, and 3 moments. But let's see, since we're interested only in this wind force, let's see if we can find the right force to find that particular, or the right equation to find that particular unknown. So I'm going to move this to get a little more room. And we're just going to start going through the equations. So sum of forces in the x. And so in the x direction, I don't seem to have any forces at all. So that's just going to be 0 equals 0. Not terribly helpful. Sum of forces in the y. So in the y direction, I have plenty going on. I'm going to have this T1 and T2, except it's not, remember, it's not entirely in the xy plane. It actually points out by about 10 degrees. And you can see that kind of over here. So let's do, it's going to be T1 times the cosine of 10 degrees plus T2, again, times the cosine of 10 degrees. And I know I have this downward force, this 10 pounds, so minus 10 and that's all the forces in the y direction, so that whole thing is equal to 0. So in this equation, T1, T2 minus 10, I don't have anything about the wind force. Let's move on to the sum of forces in the z. So sum of forces in the z direction, and I have a few things that few forces acting in this direction. So first thing I have is this wind force, and even though it's pointing to the right, remember our z direction actually, our coordinate axes, the way we set it up, it's pointing to the left. So this is negative Fw. And I again have a component of these tension forces. So this is going to be positive. Remember, this direction is positive z. So plus T1 times the sine of 10 plus T2 times the sine of 10. And sum of all those things has to be equal to 0. So at least now I've got an equation with my wind force in it. But I still have these two unknowns, the tension 1 and tension 2. I don't know those. So let's go on and take the sum of the moments. And in 3D, I need to do two separate things. First of all, I need to determine the point I'm taking the moments about. And second of all, I need to determine the axis I'm taking the moments about. So in this case, I'm going to start with the moment about the x direction, moment about the x-axis, and I'm going to choose a specific point. So this is looking down the x-axis. That's how we want to think about this. So looking down the x-axis, our moments will be, that will be a moment in the positive x direction, and the reverse would be negative x direction. So I'm looking at this point, and I'm going to take the moment about this top point over here. I'm going to call it A. So taking the moments about point A, about the x-axis, so M-A-X is how I'm going to write this out. And I can use this diagram where I'm looking down the x-axis to find the moments. So it's going to be, if I'm taking about point A, T1 and T2, those are right acting through that point. Those aren't going to exert a moment. But the 10-pound force and this wind force are both going to exert a moment. So first thing I need to do is determine some of these distances. So I've got a 12-inch long, so let's back at this. My sine was 12 inches long. Right in the middle, it's 6 inches from the bottom to the center. And so if I draw out a triangle, this is going to the middle of the sine. My total sine is 12 inches long, so this piece right here is 6 inches. And I need to find the perpendicular distance for the wind, so it's going to be the vertical part right here. And this distance right here is going to be the distance for that 10-pound force. So this is going to be 6 inches times the, since this is 10 degrees, 6 inches times the cosine of 10. And this down here would be 6 inches times the sine of 10. All right? So with that, I can kind of go back to my moment equations. So T1, T2, those disappear because I'm taking the moment through point A. But the wind force, that's going to cause a positive moment if I'm looking down the x-axis. Moments are going to be going that direction. So the wind force is going to be Fw times the distance. And the distance again is the vertical distance here, which is 6 inches times the cosine of 10 degrees. So 6 cosine of 10. All right, and I've got a negative moment, so this 10-pound weight force is causing a rotation in this direction. This is the negative x direction. So minus 10 pounds is the magnitude of the force, times the distance is going to be this 6 inches times the sine of 10 degrees. So 6 sine of 10. And that whole thing is going to be equal to 0. All right? So now I've got 4 equations, and I can actually see a shortcut at this point. So here I'm looking to solve for the wind force, and the wind force is the only force that's unknown in this equation. The rest of it, we already know all those numbers. So let's go ahead and solve this equation. That'll give us the wind force, which is what we're looking for. So Fw times 6 cosine, 10 equals 10 times 6 sine of 10. And again, these are all degrees. All right, so I do 10 times 6 times sine of 10 degrees, divide that by 6 times cosine of 10 degrees. I'll end up with a wind force of approximately 1.76 pounds. And the units actually work out in this way. So this 10 here is 10 pounds, and then the 6 is going to be 6 inches, but we've got 6 inches over here, and we're dividing by inches, so the inches disappear. So we end up with an unknown, and that wind force is equal to 1.76 pounds. And looking back, that seems pretty reasonable. If I've got a 10 pound downward force and a 1.76 pound wind force, about 10 degrees seems like a reasonable angle. So with that, we solved for the unknown and we solved our problem. Thank you for watching, and I hope to see you again.